In this interactivity, we're going to study the forces between parallel wires. Here you can see a conducting wire, Q, fixed on a piece of wood that rests on the top of a sensitive balance. The balance is set to 0, so that it measures forces on the wire that are added to the weight of the block and the wire. Above wire Q, the wire P is held fixed in a position so that it doesn't move. Now let's select vectors of P and vectors of Q so that the size and the direction of any current flowing in the wires can be displayed. Let's drag the current in P slider one notch to the left and observe the arrow on the wire. Let's select the field lines of P to show the magnetic field produced by wire P. The magnetic field has a direction given by the right-hand grip rule. Imagine gripping the wire with your right hand with your thumb following the current arrow. The fingers around the wire will indicate the field direction. Let's increase the current in P by dragging the slider to the far left. Okay, so this is the far left. What happens? Exactly, the current vector arrow becomes longer and more lines of force become visible because the magnetic field is stronger now. The magnetic field of P is made up of concentric circular lines of force spreading out from P. When the lines reach wire Q, they act in a horizontal direction from left to right. Now let's drag the current in Q slider one notch to the left. What happens? You are right. Wire Q is attracted to wire P, so the block of wood moves upwards and the balance shows a reading of minus 0.02 grams. Let's see if we can apply Fleming's left-hand rule to wire Q, where the lines of force of P are met. Well, your first finger should point in the direction of P field, which is left to right. Your second finger should point in the direction of the current in Q, which is towards you, and your thumb will then point in the direction of force on Q, which is upwards. Now, let us select the field lines of Q to see how the field of wire Q acts on the current in P to produce a downward force. Check the force direction using Fleming's left-hand rule on P. Well, your first finger should point in the direction of field of Q, which is left to right. Your second finger should point in the direction of current in P, which is towards you. Your thumb will then point in the direction of force on P, which is downwards. What happens if you reverse the current in Q? By moving the slider one notch to the right of 0. Great job! The attractive force between the wires changes to a repulsion, and the balance reads 0.02 grams. Currents in two wires that are flowing in the same direction attract each other. Currents in opposite directions repel each other. For a current of 1 ampere in two wires at a distance of 1 meter apart, there will be a force between them of a known value. However, the force is very small for such a small current. Straight wires are at a large distance apart so that the forces are measured between two coiled wires by a device called current balance.